Welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry, unit 6 thermodynamics, and in this video we will discuss about standard enthalpy of combustion, enthalpy of atomization and bond enthalpy. First come to standard enthalpy of combustion. This is represented like this: delta C H, and this is the symbol for standard. As we know, combustion reactions are exothermic in nature, that is, heat is evolved during combustion. Standard enthalpy of combustion is defined as the enthalpy change per mole or per unit amount of a substance when it undergoes combustion and all the reactants and products being in their standard states at the specified temperature. For example, cooking gas in cylinders, that is LPG, contains mostly C4H10 butane, and this undergoes combustion according to this reaction. C4H10 13 by 2 O2, it gives 4 CO2 and 5 H2O, and this is the enthalpy of combustion, standard enthalpy of combustion of butane. Again remember, this is 1 mole. In the same way, this glucose, it provides the energy in our body. When this glucose undergoes combustion in the presence of oxygen, it gives carbon dioxide, water, and large amount of energy is released, and this energy is utilized by our body to do various functions. Problem 6.9. The combustion of 1 mole of benzene takes place at 298 Kelvin and 1 atm. After combustion, CO2 and H2O are produced and 3267.0 kilojoule of heat is liberated. Okay, that is, combustion of benzene is an exothermic reaction. Calculate the standard enthalpy of formation of benzene, and these are given. Standard enthalpies of formation of CO2 gas and H2O liquid are minus 393.5 kilojoule per mole and minus 285.83 kilojoule per mole respectively. Okay, now we have to find out the standard enthalpy of formation of benzene, and formula of benzene is C6H6, and at reference state or in the standard state this exists as a liquid. Okay, first of all write the equation for formation of benzene. Okay, and as we know, for enthalpy of formation definition is clear, that is that 1 mole of benzene is formed from its constituent elements in their reference state. That's why we will write 6C in graphite plus 3H2O as gas. Then we have to calculate whatever the change in enthalpy taking place in this reaction, that will be considered as enthalpy of formation of benzene. Okay, and to calculate this we use the Hess's law of constant heat summation. Okay, and we will use, that is, enthalpy of combustion of benzene is given, standard enthalpy of formation of CO2 and H2O is given to us. That's why first of all we write the equations for these processes like this. The enthalpy of combustion of 1 mole of benzene. Again remember, when any substance undergoes combustion, it means it reacts with the oxygen, and this is a hydrocarbon. That's why always carbon dioxide and water is produced. That's why write the balanced chemical equation for the combustion of 1 mole of benzene, and that is C6H6 plus 15 by 2 O2 gives 6 CO2 plus 3 H2O, and this is the enthalpy of combustion. It is given. It is exothermic reaction, that's why we mentioned this minus sign. Now enthalpy of formation of 1 mole of CO2. Okay, CO2, that is, it is formed from carbon in the form of graphite and oxygen as a gas, and this is also given to us. Clear? In the same way, enthalpy of formation of 1 mole of water, H2O, it is formed from its constituent elements, that is H2 gas and half O2. Why we are writing this half O2? Because there is only one atom of oxygen in one molecule of water. And for this enthalpy of formation is again given in the question. Now using these second, third and fourth equation, okay, we have to use these equations. We have to bring the following equation which we already discussed, that standard enthalpy of formation of benzene. This, okay, we have to either multiply or reverse, and we have to bring this equation. Okay, now just see. In this equation there is 6 carbon, okay, and 3 hydrogen. Now just see, in case of equation 3 there is a 1 carbon, and equation of 4 there is 1 H2. We want 6 carbon and 3 H2. That's why equation 3 is multiplied by 6 and equation 4 is multiplied by 3. Clear? At the same time, in this equation this benzene is on product side, but in equation 2 this benzene is in reactant side. That's why we will reverse the equation 2. Is it clear? Reverse equation 2. Now we will get this. If we multiply that formation of carbon dioxide by 6, then at the same time we will also multiply this enthalpy of formation of carbon dioxide by 6. Now this is not remain as enthalpy of formation. We will write is standard enthalpy of reaction, and this we numbered as a equation 5. In the same way, this enthalpy of formation of H2 is multiplied by 3. That's why its value is also multiplied by 3. We will get this one. When equation 2 is reversed, okay, now when we write in the reverse form, this benzene will come in the product side, and when we reverse the equation there is no change in the magnitude, but sign of the enthalpy changed. Okay, now add the equation 5, 6 and 7. Now during this addition we can write the reactants of all these equations first, then after the arrow mark we will write the products of all these reactions. Then any species is common, we will cancel out. That's why from this we can write 6 graphite plus 6 O2, okay, and from this we can write 3 H2 plus 3 by 2 O2. Clear? Then from this we can write 6 CO2 plus 3 H2, then arrow mark. Then from equation 5 we can write 6 CO2, this is 6 CO2. Then from equation 6 this is 3 H2O, this is 3 H2O, and then from equation 7 that is benzene, C6H6 and 15 by 2 O2. In the same way we will add the value of these enthalpy change, that is minus 2361 minus 857.49 plus 3267. We are adding, okay, actually when we add this, that is this, when we add this we will get again is this negative number, okay. And when, just see what things we can cancel out. Just see, this 6 CO2 is cancelled by this 6 CO2, this 3 H2O is cancelled by this 3 H2O, okay. Then see the oxygen, this is 6 O2 and this is 1.5, that is 7.5 O2. This one and this one 7.5, that is 15 by 2. This is cancelled by this. Now what remained? That is 6 graphite, this one, this is 3 H2 in the reactant side, and in the product side this is only benzene, C6H6. This is the required equation, and for this if we solve this one we will get 48.51 kilojoule per mole. This is the standard enthalpy of formation of benzene. Clear? Now we are also having one alternate method. If we use this formula, okay, that is standard enthalpy of reaction is sum of the standard enthalpy of formation of products minus sum of the standard enthalpy of formation of reactants. We can also use this formula, and this formula we will apply on this thermochemical equation, that is enthalpy of combustion of 1 mole of benzene. Now in this case enthalpy of formation of carbon dioxide is given, Enthalpy of formation of water is also given, but enthalpy of formation of oxygen is not given. But oxygen is in elemental state. That's why its standard enthalpy of formation is 0. Now, this is standard enthalpy of reaction is equal to 6 into standard enthalpy of formation of CO2. This one. Then 3 into standard enthalpy of formation of water. Then minus in square bracket, we will write standard enthalpy of formation of benzene. This we have to calculate. And then plus 15 by 2 into standard enthalpy of formation of oxygen. Put the values. Okay. This is minus 3267, 6 into minus 393.5 plus 3 into minus 285.83. This is minus, right? This as such, because this we have to find out, and this for this oxygen this is 0. And if we solve it, again we will get the standard enthalpy of formation of benzene 48.51 kilojoule per mole. Okay, this is the another method by which we can also find out the standard enthalpy of formation using this formula. Okay. Now, enthalpy of atomization, this is represented like this. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. Like H2 gas convert into 2H gas, that is hydrogen gas molecule. H2 molecule from gas phase will decompose into hydrogen atoms, and in this case whatever the heat we are supplying, that is known as enthalpy of atomization. Again, this is a endothermic process. Okay, in case of diatomic molecules like dihydrogen, enthalpy of atomization is also the bond dissociation enthalpy, because in this case again this bond is breaking down. Other examples you can also see. This is CH4 in the gaseous state. When we supply the heat, then this will decompose to give carbon in the gaseous state and 4 atoms of hydrogen in gaseous state. Okay, these are obtained in gaseous phase. That's why this is the enthalpy of atomization of CH4. Now, if we take the metal like sodium in solid state, but if we supply the heat, then this will convert into Na gas, and whatever the heat we are supplying, this is also the enthalpy of atomization for sodium in solid state. Now again remember, this process, that is conversion of solid into gas, this is the sublimation. That's why we can say in this case the enthalpy of atomization is same as the enthalpy of sublimation. Bond enthalpy, this is represented like this. Okay, this is two type: bond dissociation enthalpy and mean bond enthalpy. First come to the bond dissociation enthalpy. For diatomic molecule we use this word. For diatomic molecules, the bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. Okay, remember, reactants are also in gas phase, products are also in the gas phase. These are the some examples. Okay, this is H2 converting into 2H gas, this is Cl2 converting into 2Cl, this is O2 converting into 2O. Again remember, it is the same as the enthalpy of atomization. Now mean bond enthalpy, this is used for the polyatomic molecules. Take the one example like in methane, that is CH4. Okay, all the 4 carbon hydrogen bonds are identical in bond length and energy. However, the energy is required to break the individual carbon hydrogen bonds in each successive step differ. See, if 1 carbon hydrogen bond is broken down, we will get these are the products, and this is the bond that is bond enthalpy. Now from this CH3, if another carbon hydrogen bond is broken down, we will get this one, and this is the bond enthalpy. In the same way, from CH2 we will get this one, this is the bond enthalpy, and last one this. Okay, now in each step carbon hydrogen bond length is different. That's why in this case we will take the average of these. Okay, therefore for this overall equation, if you find out enthalpy of atomization, add all these things. This is 1665 kilojoule per mole. That's why this is bond enthalpy of carbon hydrogen bond in methane is 1/4 of. Why 1/4? Because there are 4 carbon hydrogen bond in methane. 1/4 of standard enthalpy of atomization of methane. Okay, that's why this is 1/4 into 1665, and if we solve it, we will get this one. Okay, the standard enthalpy of reaction is related to bond enthalpies of the reactants and products in gas phase reaction as per this relationship. If we know the bond enthalpies of reactants and products, we can find out the standard enthalpy of reaction. As we know, during reaction, what happens? The bonds between reactants are broken down and new bonds are formed in products. That's why if we use this formula, standard enthalpy of reaction is equal to sum of the bond enthalpies of reactants minus sum of the bond enthalpies of products. We can find out standard enthalpy of reaction. Thank you. Subscribe my channel to get the new videos from this chapter.